Now, before we continue, let's summarize last time about the norm of an operator A. So the norm of A is the factor that the length of your vector x can be multiplied at most when you apply the operator A to the vector x. So you can express it exactly like this. And equivalently, you can also use the supremum over all x's that have norm equal to 1 instead of less than or equal to 1. This will not change the supremum. Another way to write the same quantity is to take the supremum of the fraction a, let me say, z divided by the norm of z. And now let z run over all vectors, not just the ones with norm 1, not just the ones with norm less than or equal to 1, but all vectors. The only exception is you should not allow the 0 vector, because then you would divide by 0 here. To understand this last equality, just put x equal to z divided by the norm of z, so it has norm 1, so it can be used as the x from the previous expression. Now, maybe you've heard some people speaking of continuous linear operators. What is that? Well, the following theorem says that a linear operator is bounded if and only if it is a continuous map from x to y. So these two properties seem to coincide for linear operators. Of course, this theorem needs a proof. So let's start with the easy direction, which must be this one. So let A be bounded, and then we have to show that it is also continuous. Right, so we have to show continuity, and on the way we may use boundedness. How do you show continuity? Well, you take an arbitrary sequence that converges to some limit in the sense of your first space x. And for continuity, it remains to show that also the images a, xn converge to a of x. Now we just rewrote what continuity means, but we still have to argue why it holds. So since, okay, now we still have to give the argument. So how do we check that axn converges to ax? Well, we look at the norm of the difference, because that's our metric in the space y. Okay, and now this is the point where we have to do something clever, and we're certainly forced to use the property of boundedness somewhere on the way. So let's first use linearity, because we also have that, and rewrite this as a of xn minus x. Okay, and now comes boundedness, where we can bound this by norm of a times norm of xn minus x. You remember this from this red inequality here. This is exactly what we are using now, but with x replaced by xn minus x now. Okay, but now we're already there, because we know that xn goes to x in x. We can say that this norm goes to 0, and that's why this product goes to 0, hence showing that our norm goes to 0, and therefore our operator A is indeed continuous. So as I said, that was the easy direction. For the other direction, we need some more clever thinking. Well, let's start by writing down what we have to do. So let A be continuous, and this time we have to show that A is bounded. Okay, and if you think about it for a while, then maybe you get the following idea. You start with an indirect proof. So you say, well, suppose it's not bounded. Let's think a bit for what that would mean, because we haven't seen any unbounded operators so far. Well, it must mean that the unit disk, or just the unit circle in X, must be mapped by A to something unbounded on the other side. Okay, it's clearly difficult to draw something unbounded here because your piece of paper is bounded. But you could say that no matter how large circles or disks around the origin you try in Y, they will never cover the whole image of that blue disk, the unit disk of X. Or in other words, there is a sequence X1, X2, X3, and so on in X, which is in the unit disk, possibly on the boundary, such that the images A of X1, A of X2, A of X3, and so on, run away from the origin as far as possible, so they will have a norm as large as you want. So let's say the norm of AXN is bigger than the index n, while the norm of xn remains less than or equal to 1 for all n. So this length is more than 1, this length is more than 2, this length is more than 3, this length is more than 4. Well, you can see the idea. And now the trick is to look at the following sequence. You take Zn equal to xn divided by the norm of not xn, but the norm of a xn. We will see what that brings. Well, it's easy to check that the norm of this new element Zn. So let's do this explicitly because we're doing this for the first time. So this is the norm of 1 over norm a xn times the vector xn. And now this here is just a little alpha that you can get out of the norm by putting modulus signs around. So we arrive at modulus of 1 over norm axn, and of course times the norm of xn. Now it's clear that we can drop these modulus signs here because the number inside is already real and non-negative. Okay, now this is just the quotient of two real numbers, where this one remains bounded by 1, and that one goes to infinity as n goes to infinity. So as a result, our quotient goes to 0 as n goes to infinity, or in other words, sequence Zn goes to the origin, converges to the null vector in X. Looking at the norm of the corresponding images in the same style gives you that bilinearity of A. You can get that little alpha here in front of A, and from there you can get it as modulus alpha in front of the norm, so that you end up with just this expression where, of course, again we can drop the modulus signs here because the number inside is already real and non-negative. Okay, and now we start to understand the motivation behind this definition up here, because we end up with just 1 at this point. But now from this we can conclude that the sequence A set n is certainly not going to the 0 vector, because its norm is not going to 0, it's just remaining at 1. But 0 would have been the image of the 0 vector under A, and hence the operator A cannot be continuous. It probably helps to see that proof again in a slightly more graphical way. So let's come back to our diagram from here and see what we did with our trick to introduce the sequence Zn. Well, essentially, for every xn, we divided this diagram by the length of not xn but the image A xn, and of course you also have to do that on the other side. So you multiply by that little alpha that I'm drawing here. And because this denominator here is going to infinity, this is dragging your points more and more towards 0. So Z1 is maybe here, and then Z2, Z3, and so on, like we computed, have a norm that is going to 0. So you can see this sequence indeed converging to 0, as we said before. This is Z4, of course. But what is happening on the other side? Well, we also divide by the length of AXN for every n, but that makes all of these red lines the same length, which is length 1. So the vector A Z1 and A Z2, A Z3, A Z4 all end up being of length 1. So all these green points are sitting on the unit circle around the origin in Y. So clearly they do not converge to 0. Okay, well, summarizing, our sequence Zn converges to the 0 vector in X, but its images under A, which is the sequence A, Zn, does not converge to the 0 vector in Y, but it should if A were a continuous operator, because this 0 here is just A applied to the other 0 over here. So we conclude A is not continuous, which of course contradicts our assumption from the beginning that A is continuous. Okay, and that's how the proof goes.